approach for crack modeling of elastomers. Here, I briefly applying is reporter. Specifically, it will be shown why we use phase feed and what is phase feed approach. Then, since we use phase feed to model crack in elastomer, briefly explanation of our micromechanical model, of course, of the elastomers will be shown. Then a theoretical overview of the phase field coupled with our micromechanical model will be explained. And finally, we go through some numerical examples. Let's start with the introduction. As it is known, many real physical problems involve an evolving interface whose shape and position has to be determined while solving the problem itself. This evolving interface can be of different type, depending by the physical problem that we are studying. In this sense, the phase field approach is a tool that can be used to model a sharp transition from a phase to another one by assuming it to be a smooth transition of a scalar parameter, which is called phase field variable. Here are just some examples to better understand the phase field concept. One can see in the first three ranges a physical problem, solidification of matter. One can see that when the material is in a liquid state, the phase field variable is equal to 1, while when the material is in a solid state, the phase field variable, which is S, is equal to 1. Sorry, before it was equal to 0. And during the transition, this variable can range in a smoothly way between 0 and 1. In fractal mechanics, we have the same concept, but of course, the transition of the two transitions are the undamaged material and the fully broken. So, since we use phase field to model crack in elastomer, let me briefly show our micromechanical model. The mechanical response of a polymer is connected to the state of the network, and every change of the network configuration reflects on the macroscopic state of the elastomer. From a statistical point of view, that this is the network of a polymer. Inside the network, we have a chain. A chain is made of n segments which are connected together. We call this segment Coombe statistical segment. And we can describe a chain by using a vector, which is reported here, which is a vector connecting the two extremities points of a polymeric chain. And we call this vector end-to-end vector. The statistical distribution of this vector provides all the information to evaluate the stress state in the material, is reported here, which depends by the length of the segment and by the number of the segment made the chain. We can also express this statistical distribution function with this expression, which depends by the stretch applied to the continuum body. The mechanical behavior of the elastomer is governed by the evolution of this function, which evolves according to the stretch applied to the material. We can see here, this is the probability distribution function in the deformed state, and when we stretch the material, there is an elongation of this function, obviously in the direction of the stretch. Once the chain distribution is known, we can evaluate the energy stored in a single chain by using this expression, and then by most simple integral, we can evaluate the internal energy term of the material by adding up the term of the single chain. Finally, with this expression, we evaluate the stress state in the material, which is the Cauchy stress. Okay, let's start with the focus of this lecture, which is the phase field approach. The phase field approach, it has its origin by the variational formulation of Britton-Fractal presented by Frankfurt and Marigot in 1998. This theory states that crack grows by following a path that ensures the minimization of the total energy of the system, the so-called functional of the material, which is reported here. We have the sum of two terms, the internal energy term, or the elastic energy term, and the factor energy of the material. To solve the problem, we have to minimize this functional, but as you can see, this problem is a little bit difficult because the second integral is an integral over the current crack domain, which is unknown, so it's difficult to be numerically treated. In this sense, the phase field approach provides a sort of regularization of the crack, going from a crack, a sharp crack, which is reported here, to a smooth crack, depending by length parameter, which is called epsilon. And the real crack is recovered when this parameter epsilon tends to 0. By using this regularization, we can rewritten the previous one energy functional in the so-called phase field regularization. We can see here that now the second integral is an integral over the body and not over the current crack domain, so we can easily minimize this functionality in order to obtain the solution of the problem. Just some words about the terms that are involved in this equation. I have just mentioned the phase field variable, which is equal to 1 when the material is in damaged state, while it is equal to 0 when the material is in a damaged state, while it is equal to 1 when the material is in a fully broken state. We have the degradation function, which is a function that has to act in order to model the loss of stiffness of the material. And we have the length parameter scale. As you can see here, by reducing this parameter, the smooth crack is approaching to the sharp crack, which is obviously the real crack. Also here we can see that by reducing the length parameter scale, we have a better approximation of the crack, but the lowest is the length parameter, the finest has to be the mesh to be used in our computation, so to avoid in order to reduce the computational effort. These are reported the equation of the problem, the linear momentum balance, the evolution of the phase field variable, of course coupled with the boundary condition. Notice that this equation and also the boundary condition are written in the reference configuration, and this is a most important detail to specify since we work in large deformation. Then we have to update the stress obtained by reducing, as already shown for the internal energy term, the stress by applying the degradation function. So here we have the stress that I have shown you before, when no damage occurs in the material, and here we have the stress when damage occurs in the material, and this, we have to reduce the stress by using the degradation function. Okay, only some comments. So how can we evaluate the fracture energy of a polymeric material, of an elastomer in this case? Rupture of a chain from a microchemical point of view can occur when the dissociation of one of the carbon-carbon bonds make the chain occurs. So we can imagine to relate the fracture energy of a chain to the energy to break a monomer unit. We use in this work the Lake and Thomas model of 1967. We can consider a chain inside the volume of the polymer, inside its network. This chain is crossing a plane of dark propagation, and we can evaluate the fracture energy of the material by multiplying the so-called fracture energy of a single chain times the number of chains crossing a unit cracked pattern. Here are some numerical values to understand what is the magnitude order of this value for our polymers. As you can see, by increasing the number of statistical cone segments made in the chain, that means that we have many longer chains in our network. Longer chains are less prone to fail. Briefly, numerical example, we modeled a rectangular plate with a rigid top and restraint at its bottom with an initial straight edge. The material of this plate was of two types. In the first case, we use an elastic perfectly brittle material, while in the second case, we use our micromechanical model, so we treat this plate like an elastic polymer. Okay, in addition, we use two values of the fracture energy, which are reported here. Here we can see the dimensional stress versus dimensional vertical displacement for the case of elastic perfectly brittle material. So as is expected, by increasing the fracture energy, there is an increase of course, of the peak load, while for the case of elastic polymer, the peak is almost not clear, at least for the value of for the small value of the fracture energy. In terms of crack pattern, of course, the crack is not a good approximation in this case because we have used a not fine mesh, so a length parameter which is larger, and we have a crack that is so bad. So anyway, this is the crack for the elastic perfectly brittle material, and here we can see that the crack propagates by using a mode 1, but also mode 2 appears. This is because maybe there is a rigid rotation here, because we have modeled for our commodity the top of the plate by using rigid elements. In the case of elastic polymer, as you can see, the crack are less developed in comparison to the previous one, and this shows a more productive behavior of the polymer. And that means that polymer, if we model a polymer by using a model which is more properly for a polymer, we can notice, according to the literature, that this material are more defect tolerant than the previous one, of course. In conclusion, we have developed the phase feed approach coupled with our micromechanical model. We have evaluated the macroscopic fracture energy on the base of a micromechanical model and not by using experimental values. And there is to underline this aspect that with the phase feed approach, we are able to solve the problem and to simulate the crack propagation without any intervent on the mesh, so we don't need a remeshing or like that. So thank you for your attention.
You may